if you have a constant coefficient linear homogeneous differential equation like this one, how do you solve this? It's first write down the characteristic equation. Then you solve this using either factoring or a quadratic formula. And there are three cases, right? Case one, when R is A or B, where A and B are not equal, what solution satisfies this? In general, it's y equals to, oh, I shouldn't be using A and B because I already have it here. Let's just say R1 and R2. Okay? R1 is not equal to R2. So the solutions look like C1 times e to the R1x, C2 times e to the R2x, right? That's the general solution. What if you get two solutions, but they turn out to be the same? So sometimes if b squared minus 4ac is 0, when the two solutions you get is just a single real number, right? What do you do in that case? Well, one solution is this, R1.
The second solution should be time R.
Not times R, it should be times X.
Oh yeah.
It's times X, right? Okay. I mean, this PDE course relies on your ordinary differential equations course. I'm only writing this because I know some of you forgot, and you may have taken this like 2 years ago. Well, you're supposed to know this. If you don't know it, then you will have trouble, okay? So you should review this part. And of course, there's my YouTube channel. You can always go there and watch how I explain these. Okay, case 3. What if R is like alpha plus minus beta I? Okay, you can have a complex set of roots, right? If this is negative, then you get complex values. In that case, you could plug this into here, and we know what to do with e to the ix, right? There's the Euler identity that we can use. But writing your solution that way is not advised because that would create functions that have complex values. Right? So instead, what you do is you take the real part of that function and the imaginary part of that function that you get by plugging these in, and create separate functions that will create real values. And the end result is that you get y equals to e to the alpha x c1 cosine beta x plus c2 times sine beta x. I explained that the way you're getting these solutions are not really solving, it's more like guessing, right? You just solve this, and what you're doing is you're plugging in something called an Ansatz. Ansatz. It's a German word for, I think it's called a sentence. You say, these always have this as solutions. You plug that in, and if you differentiate twice, R comes down twice, right? So you get r squared. When you plug this in, you get r. You get plug in that in, and you don't get an r, so you get an equation which is the characteristic equation. And once you get those values, plug them in, and then say, hey, this will solve this equation for those values of r. The reason that kind of argument is justified is because we know that second order constant coefficient homogeneous differential equations will always have a solution for initial values. So the initial value problem should be y of 0 equals to something m, and y prime of 0 equals to n. If you provide the value of the function as 0 for y of 0 and y prime of 0, then there always exists a unique solution for any two choices. And then that's why if you see the solution, you get C1 and C2. Because if you need to satisfy, if you need to get a unique solution for two initial conditions, then you better have exactly two free parameters. It would be very strange if you just have 1 or 3. It has to be exactly 2. That's why you have C1 and C2. And that's what happens here. If you have R1 and R2 the same, then if you didn't have the x, then these two will be the exact same thing, and it will fail to satisfy that initial condition. That's why you need to invent the second solution. It happens to be that if you multiply by x, it does work. So again, you get two free parameters. Okay? And again, you have two free parameters. Which also says if you had like dy triple prime, then you would probably have three functions, right? With C1, C2, C3, right? Yeah. So you have to have the same number of free parameters as the order of the differential equation. That's what happens. Okay? But then, I want you to think about this other type of endpoint value problem, which is, here's an example. If you have y double prime plus, let's say, 2y prime plus 2y equals to 0. And let's say y of 0 is 0. And then y of pi is 2. Now, do you see that this is a bit different than an initial value problem? Yeah. What's happening? I'm not giving you all the information at a given point. Rather, I'm providing the value of the function at two different points. Okay? So that's why it's called an endpoint value problem. So basically the idea is that y of 0 is given, y of pi is given. So two endpoints are given, and then inside the interval, you're saying that this condition must be met. And now you have to find the solution. Okay? Let's see what happens if you try to solve this. R squared plus 2r plus 2 equals to 0 as before. Right? And then if you solve this, you get r equals to 1, negative 1 plus minus 1. So according to this third case, your y would be e to the negative x times c1 cosine x, right, plus c2 sine x. Okay? Now let's see what this condition gives us. Y of 0 would be, what? Sine 0 is 0, e to 0 is 1, cosine 0 is 1, so what do you get if you plug in 0? You just get C1. But C1 is given as 0, so this must be 0, right? Okay? So C1 0. Now let's plug in y of pi. What's sine pi? 0. Cosine pi? Negative 1. E to the negative pi is e to the negative pi, so you have negative e to the negative pi times C1.
Is it -1 plus minus I?
Plus sorry. Oh, 1i. Yeah. Okay. So I meant that alpha and beta are 1, okay? Alright. So you have y of pi as this, but we just said C1 is 0, right? So this will be forced to be 0. So there's no way that it can be equal to 2. Right? So what just happened?
Such solution is not the same.
Yeah. There is no solution to such a endpoint value problem. Okay? Yeah. Because I know that if such function did exist, right? If such function did exist, then y of 0 and y prime of 0 should be some value, right? Then your solution must look like this, right? But there's no such function.
So that's why it's the initial points are given with the one derivative and one just regular.
Yeah, if you're given any question that looks like this, then the solution is always unique. There always exists a solution, and the solution will be unique, satisfying the other. But that's not true for endpoint value problems. Okay? Sometimes you might not see a solution. Okay? Now, what if instead this one was given as 0? So let's just say example 2. So example 2 is y double prime plus 2y prime plus 2y equals to 0, right? And then y of 0 is 0, and y of pi is 0. Then what?
Many solutions exist.
Right, because, see, both of the conditions will just force C1 to be 0, right? The solution will be exactly the same as this, but both conditions, this one will say C1 is 0, this one will also say C1 is 0, and that means C2 can be anything, which means that anything that looks like e to the negative x times C2 times sine of x will satisfy both of these conditions. Of course, sine of 0 is 0, sine of pi is 0, so it's going to satisfy both, right? And this equation, it does satisfy this differential equation. So you can have infinitely many solutions. And of course, there are examples. If I had y of 1 as, so if I have example 3 where now instead of y of pi equals to 2, if I put y of 1 equals to 2, then the solution looks ugly, but it still does exist. There will be one unique solution. Okay, so the peculiarity of the endpoint value problems is that sometimes you may not have a solution, sometimes you may have infinitely many solutions, or sometimes you might just have one solution. Okay? There are only 3 of those cases.